back from break. That's really what it is. Me or you? All right, so we're gonna go ahead and get started. If you'll recall, before we left for break, which probably for many of you feels like forever ago, a lot of things happened between then and now. You know, Thanksgiving, Turkey Bowl, all that good stuff. But in between then and now, we had a lesson. And we had only missed the last two questions of the lesson, which I put into today's slides to make sure that I cover. And you have a homework, and that homework is due on Wednesday. So don't forget there is homework due on Wednesday. I'm not available for tutoring after school today, but I will be staying tomorrow after the planning meeting if you have questions about that homework. I do want to bring up, I did the homework yesterday, and there is one repeat question. If you did the homework, you know this. Question 6 is a repeat of an earlier question, so you can skip that question. So skip question 6. That's how this day is going to go. So we're going to go ahead and get started with the lesson. And yeah, your favorite numbers will show up at some point. Yay! Okay, so this question is actually really recent. I think this is from the 2025 exam, like from the exam that was just given. And they give you the rate law. If you'll recall, this is called the rate equation. That means they're telling you how much each reactant contributes. And they say, in first experiment, the initial rate is measured starting with known concentrations. In a second experiment, we increase each of these by a factor of 4. How would that affect the rate? So the way to comprehend it is you would plug the number 4 in for each of the concentrations. Because whatever the original is 4 times that. You plug the number 4 in for both. So it ends up becoming rate equals K, 4 to the first, because it's to the first power, 4 to the first, because it's to the first power again. So you'd have 4 times 4 would be 16. So the initial rate would change by a factor of 16. The K doesn't change, but the concentrations change. Welcome back. So when it says predict how, if you said just that it increases, it wasn't good enough because they told you by how much each of the reactants increased. So you also have to give how much the entire rate increases as well. So you got to be careful with that. The next question, also pretty recent. I think this was from 2023, but also within the same exam series. Fluorine reacts with chlorine dioxide. And then they tell you the rate of reaction is first order. And here's where some of you went wrong right away. Reading. They tell you in the first sentence the orders, which means they've given you the rate equation, actually. You did not have to do any math to figure this out. You just had to read it. So it says the reaction is first order with respect to F2 and first order with respect to ClO2, and there is no catalyst. So the rate is K, F2 to the first, ClO2 to the first. And the overall order of the reaction is, what are you going to do? Add the exponents. So 1 plus 1 equals 2. You had both of these correct for one measly mark. Last question here. We did something like this in the last lesson where you plug in the numbers to figure out what is the rate. So they've given you the K is 1.22. They've given you the concentrations for both. So you literally just have to say rate equals 1.22 for K. And then it's 2 times 10 to the negative 3 times 2 times 10 to the negative 3, which I plugged in my calculator as 2 times 10 to the negative 3 squared, I'm pretty sure. And then a lot of you got this correct. It was 4.88 times 10 to the negative 6. And they said a minimum of 2 significant figures is what you needed in order to get the mark for sig figs. So that's what I got. This is where we left off last class. Where we actually left off was we started looking at where we would compare experiments to figure out the orders of reaction from different experiments, which is where we're going to continue today. But today's main goal is graphing. So we're going to be graphing a lot today. Yes, Chelsea? What?
Like for the rate equations?
Either way is fine.
Okay.
If you had put the actual number 1.22 there for K, it would also be correct. I am passing out rulers to get us ready for the day because we will be graphing today. You will also want a pencil because when you graph, you should not be graphing in pen. You should be graphing in pencil. Same thing for the Cambridge exam. All graphs should be done in pencil.
Oh yeah, Daniel. Are you ready for the? Well, I think there's fascinating. I mean, like there was like a Jeopardy last class. There was a Jeopardy last class. Was there? Yeah.
I was there.
That could be an indicator of test.
I remember thinking it was like,
See? What he's gonna do?
Oh. They might be stricter in that course with graphing because it's an easier course. So they just like the easier the course, the stricter they are with certain things. All right, so Unit 4, Part 2. Today we're going to be continuing rate of reaction calculations, but we will be focused on graphing for much of the lesson. And so if you take a look at our standards, it says same thing as before, explain and use these different terms. The only one that's new today is half-life. So we're going to go over half-life today. Half-life, I believe the year that I taught your pre-ACE class, I didn't cover that topic in nuclear chemistry. It's not a difficult topic, but you'll see what it is today. You can either establish half-life by taking half of the amount you have and halving over and over and over again, or there's a formula for it that I'll also share with you if you prefer to use it in formula format. And then next class, we're going to go over rate determining stuff and intermediate. So we're breaking up the definitions when they show up in the standards. And so our learning objectives today, we're going to continue to use rate equations. Remember, we only need to use the exponent 0, 1, and 2. They will not be giving you any other exponents than that. Trying to make it as easy as possible. Deduce the order of a reaction from concentration time graphs or from experimental data. We started looking at experimental data last class. We'll continue that today. And we're also going to look at how to determine order of reaction from graph. And the half-life method is what we'll need to use for graphing. We're going to look at experimental data in graphical form. And we're going to calculate initial rate using concentration data. We've started this last class, D&E. So these are all parts of the same standard. And then 26.1.3, half-life is independent of concentration. I have a video that I just put up on the classroom. If we have time, I'll show it today. It's Professor Dave. I don't know if you've ever seen Professor Dave explains. He's pretty cool. Professor Dave does a lot of the AP Chem type stuff, and he has a good explanation on this topic. So if I have time, I'll show it. If not, it's on the Google Classroom. I put it up in the resources. And then use the half-life of a first order reaction in calculations. It's nice that they only ask you to do half-life for first order reactions because that is the easiest equation. But they do leave a lot out in this topic that's covered in AP Chem. Kinetics is like, this to me is a watered down version of kinetics compared to what you get in AP chemistry. So if, for example, you're studying for the ACS Olympiad, there would be other equations and formulas that are beyond what we cover here that you would also need to be looking over. So if you rented out a textbook from me for the year, look at the kinetics chapter. There are additional equations to that from what you'll see from Cambridge. Talking about schedule real quick, I have a bunch coming up for what's going on in our class. But first things first, I'm going to be out this Friday. If a couple of you already know that, I got, we like to use the word voluntold. I got voluntold to do something that requires me to be in Hialeah all day on Friday for the school. And so I will not be here on Friday. I also won't be here Monday the 15th. So that makes our schedule the following. We are likely going to finish our lessons before we leave for break. So by the 17th, my goal is to be done with the lessons for the unit. But we're not going to have the test until we come back from break. So I'm giving you that heads up. You are going to have to, I'll give you an optional winter break packet to do for some extra credits.
Yeah.
And we will have the test when we come back from break. But I never give the test the first day we come back from break because that would be terrible for everyone. So it will be on the Thursday when we get back from break. So you'll see that it's on the calendar for January the 8th. A week after that, January the 15th, is your second quarterly. So you know that that's coming up, and the quarterly covers all 4 units. So that's about 2/3 of the curriculum, actually. Yes.
Was that go to the second quarter or third quarter?
Everything is second quarter. Everything is second quarter.
How many weeks after the break or the school?
2 more weeks after the break.
About 5 weeks in between.
There's 5 weeks left in this. Yes. 3 weeks and then 2 weeks after. All right. So that's going on schedule wise, just so you're aware. I will be giving you back your tests on Wednesday. So for your Unit 3 exams, you'll get those back on Wednesday. And then, like I said, on Friday, I won't be here, but I will give some practice questions for you to do so you can practice kinetics, because after Wednesday, we'll be halfway done with the unit, actually. So like I said, because I'm going to be out a couple days, the second half is going to move kind of slow, but we should be finished with it before we leave for winter break. It's good news. And then what I decided to plan to do is that on the day we go for winter break, on the 19th, we will have a lab that day that will afford you the ability to, if you are leaving early for like a vacation or something, we won't do a lesson that day. We will do a lab that day. So that's going to happen on the 19th, which is the very last day before winter break. Yes.
I was gonna ask if winter break starts the 20th.
Winter break starts the 20th. Yes. 12/19 is a Friday. It's the very last day of school for this year, for 2025. All right. So let's go ahead and get started. This is actually where we left off. We did this question before we left for break. This is the very last question that I rushed through. But if I recall, I covered this, but I didn't cover the questions that came after. So we're going to use this to review how to use experimental data to come up with rate equations and orders. So do you remember the strategy of what to do here? What would we do?
The proportions.
Kind of a proportion thing, yes, Ramon?
Essentially, we're gonna have to find for one of them 2 of the same.
Find 2 experiments where one concentration stays the same and another concentration changes. And then see how does that affect your rate? Yes. Analia Morales, I do. Analia, come here. Okay, so pick 2 experiments where one concentration stays the same and one changes. I'm going to go ahead and choose experiments 1 and 2. That leaves NO the same and it changes the concentration of oxygen. The other thing I do is I always take the bigger number and divide by the smaller number. So I'm going to say the oxygen, so for O2, it's going to be 0.024 divided by 0.012 equals 8.15 times 10 to the negative 3 over 4.08 times 10 to the negative 3. 2 equals 2. What does that tell me about the order of oxygen?
It's 2.
When I double the concentration, I double the rate. The order must be linear, right? So the order must be 1. So order equals 1 for O2. And then I'm going to write a line here, and then I'm going to do NO. So what do we do now for NO? Which 2 experiments should I choose? I choose 2 and 3. because that keeps oxygen the same. So that gives me for NO 0.064 over 0.032 equals 3.28 times 10 to the negative 2 over 4.08 times 10 to the negative 3, 2 equals 4. So when I double the concentration, I quadruple the rate. What does that mean the order of NO must be?
2.
Yeah. So NO order must be 2. We actually did this question, like I said, before we left for break. So we're going to go ahead and continue. Question?
It's about the hamburger stuff.
You can ask later, yeah. All right, so continue. Write the rate equation. So this would be rate equals K NO to the second, O2 to the first. It doesn't matter which of the reactants you write first or second, just that you have them right.
Wait, if you
Yeah.
put the over.
Plug it in. Calculate the value of K. So how would we do that one?
You can put concentration and then put a rate that it shows you.
So you pick any experiment, doesn't matter which one, except for experiment 4, because you don't have enough information. And you would plug in the initial rates and the concentrations and use that to calculate K. So we usually pick the first experiment, but it doesn't really matter which one you pick. So I have 4.08 times 10 to the negative 3 equals K 0.032 squared and then 0.012. How do we solve this? Yes?
How can we give NO the power 2 exponent because of the number in front, even though in the bell work we didn't do?
Because we did it here.
Oh, never mind.
The orders too. We're using the orders here to come up with the rate law. It does not have to do with the numbers in front here.
Right.
Last class, I told you that it would only if it said we had a one-step mechanism, and that's not mentioned here, so we wouldn't know from that. The only reason we know it's 2 is because we calculated that in part 1 from this data. That's how we know NO is 2, because that's what the order is. All right, so we plug this in. Solve for K. Yes, Chelsea.
Why is the denominator of the equation on the
I'm sorry?
why is the denominator for the equation on the right? Like, why is it 4.0? Are you using that instead of the 8?
Oh, you're right. I just plugged in the wrong number. 8.15 times 10 to the negative 3. You can fix that. It should end up being 2 equals 4 when you do rate of the third over rate of the second. And then that gives you 2 equals 4, which gives you the order of 2. Now what is K? How do we solve that? Ramon, go ahead.
K, and then we choose a random experiment like 0.032 square.
Okay.
Basically, we divide the equation. We divide the initial rates over the concentrations.
Yes. So it's the concentration of the one we pick. I picked experiment 1, and I divide that by the concentrations. And the rate that I got for the value of K is 332. See if you did the same. And it doesn't matter which experiment you choose, experiment 1, 2, or 3. The whole point of K is that it's going to be the same, regardless of which experiment you choose. So whether you chose the values of concentrations from experiment 1, 2, or 3, does not matter. K stays the same. What affects K again? Do you remember what does affect K? Because concentration doesn't. Temperature does. Temperature and pressure, technically. So assuming same conditions, this would always be the K for this specific reaction. Find the initial rate of experiment 4. How would we do that final part? So now we've got concentrations, we've got the K, and they left this blank on purpose because they want us to find the rate of experiment 4. So we would then once again plug in rate equals, this is my rate equation. My K I now have a number for. The number is 332 because we found that in the last step. My concentration of NO for this is experiment 4 is 0.096. That would be squared. And then 0.036 here. That would be to the first. And then I just plug in all the numbers. And I got 0.110. See if you get the same. Rates equals 0.110. And do you remember what were the units of rate again? Just in case you were asked. You should know the units of rate are mole DM minus 3, S minus 1. It's concentration over time. All right, so that was one of the questions we had not finished. And then the next question I really wanted to show you, because this is one of the unique situations. There's 2 unique situations that will show up in your homework. One of them is the one I'm about to show you. The second one I realized I didn't put any questions about, but I will bring up exactly what the situation is after we do this question. All right, so final question before we get to graphing. In this situation, you're not given, you're given where the OH minus doesn't change and the CH3CHO changes, but you're not given the opposite situation where OH minus changes and CH3CHO does not change. So how would we handle that? They kind of try to lead you in the right direction by telling you which order to solve for first. It says deduce the order of the reaction with respect to CH3CHO. So what experiments would we use? 1 and 2. So 0.2 over 0.1 equals 2 over 1. So 2 equals 2. Deduce. Does that mean I have to say much with the command word deduce? I don't. It does not say explain. It does not say that I have to discuss this. So literally all you have to say is the order is 1. Does that make sense? You don't have to show the proof. They're expecting that you understand. When I double the concentration of this, I double the rate. They made the numbers easy on purpose. And so the order must be 1 as a result. All right, deduce the order of the reaction with respect to OH minus. This is the harder part. There's 2 experiments where OH minus changes, but CH3CHO also changes. So how do I figure this out? Anybody have an idea? Go ahead, Ramon.
Because we already know that CH3OH like changes by a factor of 2, we divide the initial rate of reaction by 2 to just kind of separate like.
That's a good way to approach it. Yeah, that makes sense. Ramon said that because we know when the concentration of CH3CHO doubles, we know the rate already doubles because of that. So we know that if this doubles 0.2 to 0.4, then this would change from 2 to 4. That makes sense. So you could approach it that way and say, okay, so if I know that this will double the rate and it changes it from 2 to 4, then how would doubling OH minus alone change the rate? From 4, which we already know it is, to 8. What happens to the rate there? It doubled, right? So doubling the concentration of OH minus also doubles the rate because the rate is doubled twice. That's why it goes from 2 to 8. 2 times 2 is 4, and 4 times 2 is 8. And so the answer here is actually the order is 1 as well. Does that kind of make sense? So the idea that Ramon mentioned was isolate the fact that you already knew, and that's why they led you in the right direction to figure out CH3CHO first. Isolate this out, and then you'll get what's left. How could you have approached that mathematically? If we had said 0.4 over 0.2, right, times 0.035 over 0.030 over 0.015, we don't know what this is, right? Equals to 8 over 2. What would this do?
On the other side.
So this would become 2 to the first point. This would become 2 to the s, and this would be 4. So what would happen here? Mathematically, understanding algebra, this has an x in the exponent because we don't know what that order is yet. So then we would divide both sides by the number in front, which is 2. And that would give us 2 to the x equals to 2, which must be 2 to the first, x equals 1. That's technically the math that proves what I just said here. Do you have to show that math for Cambridge? You do not, because the instruction was not calculate, it was deduce. And although this is actually how I learned how to do these questions in my university classes, you do not have to use this method to solve. They just expect that you understand the idea of proportions in order to solve. But it does lead to something. If orders are in the exponent, could there be a situation where you would have to get, not in Cambridge, but just in general, in physical chemistry, for example, where you would have to get x out of the exponent by maybe adding ln's to both sides? Could that be a way to actually solve this if it was more complicated than the numbers that they're giving us? Because remember, they kept everything easy for us on purpose. They kept it to 0, 1, and 2 because they believe you can deduce that in your head without having to do advanced math to solve. Make sense? But if the numbers weren't so easy, there would be a path. All right, so these are the first 2 parts. Something I want to bring up. It says state the overall rate equation for this reaction. So it's rate equals K CH3 CHO to the first, OH minus to the first. On the mark scheme, the answer key, every time I see a question like this, it says ECF. What does that mean? That means if you couldn't figure this out, like if you couldn't get to what we had deduced here, because that is the hard question, you could literally just put a random number there. It'd be wrong. 0, 1, or 2. You got technically a 1 in 3 shot of being right. Right?
Probably 1.
0, 1, or 2, right? And then whatever number you put here, as long as you put that in your rate equation, you're going to get the answer correct. That's what it means by error carried forward. They also ECF the rest of the way. So that means that even if you had the wrong information here, because they expect that you might get that wrong. You might not be able to do this. That's the hard question. If you can take that information and then just roll with it, they're instructed to give you the point, as long as you do the other parts correctly. Yes?
I think we can do it backwards. No, never mind. You don't.
I don't think
Yeah.
so. State the units for the rate constant K. So state the units. Do you remember that? Yes.
Yeah, I think isn't it like mole 2 dm minus 9?
Not quite. So remember to do that, you would be incorporating this method, which is you would say mole, it's mole dm minus 3, s minus 1 equals K mole dm minus 3 to the second. Why to the second? Because the overall order is 2. So then we would divide both sides here by mole dm minus 3 to the second. If you recall, we did this before break. And what are we supposed to do now? It would be 1 minus 2. So it'd be mole dm minus 3 to the negative 1, s minus 1. And what would that give my final answer as? Mole minus 1 dm 3 s minus 1. Those are the units, okay? I find this to be an interesting question that they only ask for the units and they don't ask for the number, because you can't solve part 5 unless you have the value for K.
I mean, I think you can technically.
Can you?
Yeah, because
I guess you could
Yeah.
if you, Ramon, you got it. I guess because you did the homework. You're
yeah, I
on
was
top.
like looking at the question.
Hello, this is Sleep. I mean, they're in the middle of a lesson. How long will it be? Okay, no problem. Okay, no problem. Okay, Shahada and Omar, when the lesson is over, go see Miss Garcia at the end of the lesson. She said it was just a quick question. Ramon, carry on with that. Explain how you would come up with the answer.
So essentially, because we know that it increases by like a degree of one, an order of one.
The order
Essentially-
one for both, yes.
Essentially, that means that we could simply multiply the concentration by like a flat number by like, let's say, for example, we multiply the first equation by 3, first concentration for.
Okay.
We basically multiply the initial rate of reaction for the first one by 3 as well,
Would it be by 3?
because it's 0.1.
Because I think it would be, I got that one. For OH minus, wouldn't it be doubled?
Yeah, double.
So it would be not by a factor of 3, it would be by a factor of
2 as well,
2.
which is 6.
And the answer is 6. You're absolutely correct. That does work. You can do that. So what did Ramon say? And that's actually less work than what I was thinking. So I like that. Because we know that the order for both of them is 1, if you look at the fact that they gave you initial rate, they gave you simple numbers. If I triple the concentration of CH3CHO, that should triple my rate. So it goes from 1 to 3. And from 0.015 to 0.03, I double the concentration. So that should technically double the rate. So if I triple the concentration of one and I double the concentration of the other, it would be 3 times 2, because the order of 1 for each would give me an overall answer 6. Yes, Andrea. Because 0.1 to 0.3. 0.3 is triple 0.1. If the deduction doesn't work for you, what would the alternate pathway be that I was going to go with? Pick an experiment, solve for K. So if you can't figure it out this way, if that didn't work for you, there's another pathway. Find what K is. So I'm going to erase some of the stuff here to do that. Because technically, this part, it didn't have to show. But I just wanted to remind you how we did it last class. So if you can't figure it out this way, the first thing you would do is solve for, find K. Pick an experiment where you can find K. I'm going to choose experiment 1. So plug in the data for experiment 1. So 1 equals, because that's the rate, K, 0.1 to the first, 0.015 to the first. And that will give me K. So I divide both sides by 0.1 and 0.015. I get 332, I believe. Let me just double check. No, I get 667. This is the one.
667.
Yes, I do. So that will be actually the K here. So then once I have the K, what can I do to figure out the rate of reaction? Now I can do rate equals 667.3 times 0.03. And when you do that, what number do you get? Plug it in your calculator, see what value you get. 667 times 0.3 times 0.03. What answer should it be?
6.
It is 6. And I mean, rounding might make it 6.003 or whatever, but 6, which is the same thing that, Ramon, you accurately without solving for K. But that's probably why they didn't say you had to solve for K, because you could technically deduce it, maybe. Which is actually very similar to the first bell work question. The 16 times one, very similar to that one. Any questions? Any more questions on this one? No? All right, so before I go on, I do want to bring up one scenario that when I was doing your homework yesterday, I realized that this scenario is not in the lesson notes, but I do want to bring your attention to it. And by the way, the homework for this unit is very long. Not just like today's lesson, just in general. It's a very long homework.
What time then?
I did give you more time.
Think about.
Oh,
So Wednesday?
Yeah, till Wednesday. No, I'm saying the homework in general, not for this lesson, for this unit is long. If you count the amount of pages, it's a lot. Not for today's lesson, I mean like for the unit. And I did give you more time for today's lesson. It's not going to be due till next week for lesson 2. I've been giving extra time. All right, the question is question 2. In question 2 in your homework, you have a specific situation that will show up that I'm not going to address in a question, but I do want to bring to your attention. The order of one of the reactants is 0. And the reason you're going to get there is because you'll figure out the order of one, and then you'll see it doesn't matter what you do to the other reactant, that never affects your rate. And so the other situation where the numbers might change and you can't figure out what's going on is if the order is 0. So for question 2, just so you're aware, you can come ask me about it during tutoring tomorrow, but question 2, the order of one of the reactants is 0. Use that to help you figure it out. So I'm bringing that up so that you hopefully don't get as confused with it.
Like, okay. Let's say we have I2 there, right?
Yes.
Yeah, I2.
Lesson 1. We did finish lesson 1. That was all lesson 1. We are now starting lesson 2.
We have it to decimal 0. What happens?
All right, so how do we use a graph to figure out the rate of reaction? Some of this will also be review from last year. Some of this will be new. So last year in AS Chemistry, we actually did go over graphing and kinetics. We did it in one lesson. It extremely rarely shows up on an ACE exam. Very rarely, but it shows up all over the place in an A-level exam. So most of the examples with graphing will be in the A-level content, not the AS. But we did go over how to do this back in AS Chem. They give you an experiment and they give you experimental data. And then they ask you the following question, and this may actually be a repeat question from AS Chem because I have very few to pull from. Use the graph to determine the rate of reaction at specifically 80 seconds. Show all your working. So if you remember how we could use a graph to find a rate at a specific period of time. Isa.
Can you draw the tangent against the first line?
You draw the tangent line at that point. That's absolutely correct. So you've got your rulers for a reason. I am not good at drawing tangent lines on a board, but I did solve all of these on paper in advance. So I'm going to take a look at where I drew my tangent line. So I can try to mirror that. And they do give a little bit of room for error, but you should get like a slope that's kind of like this. Something like that. That is terrible. Like mine is terrible. With the tangent line, you should never cross over the black line. That's still terrible.
Because you don't have a straight English.
Mm-hmm. Close enough. Close enough. And then let me do the other side too. Try the other side. Because I did have a straight edge at home, so I did it at home. Something like that.
There.
All right, so I had gotten from the one at home, I had actually gotten my line crossed through 0.4. I'm checking yours. and yours are anywhere, it looks like from 0.38, 0.4, 0.42, it looks like. So somewhere in this general area is where you should get your tangent line. And so what are we supposed to do with this information?
It's a little bit long.
To find the rate.
No, but
Y cube minus y1.
that isn't a minus x touch.
So the rate is the slope of that tangent line. So how am I supposed to get the slope at some?
Y2 minus y1.
Yeah. So we do y2 minus y1 over x2 minus x1,
It's
where we need to pick two coordinates. Most people will choose the x and y intercept. Yes.
Will we have to like write down that formula for a mark?
No. Mm-mm. It would not be worth a mark. So when I did it, I had gotten 0 and 0.40. But if you got 0.38, that would be fine. And then I got 158 and 0. Okay. So then what would we do from here? Zero minus 0.4, 158 minus 0. Should my rate be negative or positive? Do you remember from I get 0.00253? The answer here is negative, yeah, but that's talking about a reactant. Reactants will always decrease in concentration, but a rate of reaction itself should always be positive because the rate of reaction is the rate of making products by definition. So technically, even though the answer we get here is negative in terms of the slope, we need to flip that to positive because we're being asked for rate of reaction, not rate of disappearance of reactant. If we said rate of disappearance of reactant, then it would be a negative value. But because it's rate of reaction, it's rate of making products. And so that's why we change it to a positive value. I don't know if you remember, but I did tell you that back in AS chemistry when we did maybe this exact practice question, maybe a different one. All right, what about the units? What would be the units of rate? We're always the same. Change in concentration over change in time. So mole, dm minus 3, s minus 1. 1 mark for the unit. 1 mark for the calculation of the rate. Correct. All right, so that's actually something that we had done before, and there are some homework questions, I believe, where you are asked to do this and some recent questions, so I will get one in Bellwork by next class where you have to do this. Yes. That's the tangent line. So yours may not have been exactly there. It could have been 160, 156, but it should have been somewhere in this area. So they give a range of acceptable values. Depending on how you drew your tangent line, when you draw your tangent line, just remember it should be straight, it should be with a ruler, and it should bounce off at this exact point, but not go through the black line. As long as you've drawn that correctly, they'll give you the point. Okay, so how to identify order of reaction from a graph. This is what our main goal of the lesson is today. First thing you have to do is plot a graph of your reaction rate versus your concentration of one of your reactants. Then you could also plot a graph of your concentration of reactant against its time, or, and this is what is in the standard, they want us to use successful half-lives from graph of concentration against time. And so we're going to learn how to do that today and what in the world is a half-life in the first place. So on the next few slides are a couple of graphs, and you do have to understand the reasoning behind these graphs, so I'll explain it. And it actually is similar to some things you might be aware of. Graph of reaction rate versus concentration. This is actually the rate versus time graphs. So rate of a reactant or rate of a product versus time, reaction rate versus time. If I have a zero order reaction, this means rate equals K A to the 0. It is a straight line. Why?
What did you have for one day?
This is just saying overall order of reaction. So I mean, you could isolate each one and see how they contribute and then add them together for the overall contribution. But we're trying to keep it as simple as possible. So this is just rate equals K, whatever I have to the 0 power. If this is to the 0 power, that means that rate would just be equal to K, which means you've got a constant. And if the graph is constant, that means that whatever your K is, your rate will be as well, independent of concentration of reactants. So if you understand math, that's just the line of Y equals a number, right? First order reaction, that's rate equals K A to the first. So this is actually the graph of Y equals X, isn't it? This is like just the standard graph of Y equals X to the first, because this is rate equals a number times whatever this is to the first. I'm just saying the same thing. So rate equals Y to the first. It's the graph of X equals Y. Right? When one goes up, the other one goes up by the same amount. Or Y equals X. Order doesn't matter, but I guess I should write it Y equals X. So this is actually Y equals a number. This is Y equals X. And then what about second order? What's happening here? This is actually 1/2 of a parabola. So this is the graph of what? So this is Y equals X squared, just to give you the idea, where we only use the positive values, not the negative values. So far, looking so good. So this is basically just saying, in a first order reaction, it's a linear relationship. When the order increases, when the concentration increases, the order tells me that the rate will increase by the same amount. Here, when the concentration increases, the rate will increase by an exponential amount. And so you've got to be aware of these graphs, because Cambridge could just ask you to write the general graph for a first order reaction. And then they expect you to just draw a line like this. And so looking at the concentration of a reactant versus time. So the difference in these graphs versus the difference in this graph. This is the overall reaction rate over time. So reaction rate over time. And then this set of graphs they also want you to be aware of. This is the concentration of a reactant versus time. And so in the zero order reaction, as time passes, the concentration of reactant decreases linearly. So this is a Y equals negative X slope, right? Something like that. In a first order reaction, it actually decreases exponentially. And in a second order reaction, the concentration of your reactant decreases exponentially even more. And so an interesting thing is if you understand the integrated rate equations, which is why I want to show you the video later on, if we have the time, it helps explain this a little bit better because Cambridge seems to leave some information out here on how we get here, but they want you to utilize this concept of half-life to come up with the understanding of what's going on. Yes?
Question, if we're using the concentration versus time, and we have a reactant that has order 1, no, sorry, order 0, shouldn't it be, because it's a spectator, no, it's not contributing to the reaction?
It's still reacting.
It's still reacting?
It's just not affecting the rate of the reaction. If it's a reactant, it's reacting.
How can someone react, something react to the different rate?
It doesn't affect the overall rate. It does, so it's, maybe the next lesson will answer that better for you. But it doesn't affect the overall rate of reaction, but it could still be a reactant. Yes. All right, so half-life. This is a definition, the only definition we need to learn today. Half-life in kinetics is the amount of time, it's always an amount of time, for the concentration of the limiting reactant, the one that runs out first, in a reaction to decrease to half of its initial value. So half-life, it's an amount of time. Amount of time to have half the amount you start with. And so conceptually, hopefully it's not that difficult of an idea to understand. If I start with a concentration of 1 molarity, the half-life is whatever time it would take me to go from a concentration of 1 to a concentration of half of 1, which is 0.5. This amount of time would be your half-life. Each half-life will half the amount. So each amount of time that passes, the amount you have will go down by half. So if you take a look at this question, it says, given the following information, what would the concentration of our unknown be after the 8th half-life? What would you do? Each half-life means you half the concentration. So how many times would you have to half the concentration? You would divide by 2 how many times?
In the power of 8.
8 times. So you would just take 1 and divide by 2 to the 8th. That's absolutely correct. So what would that give you? I get 0.00391. And that's mole GM minus 3. So in pre-ACE, I think I did not go over this formula in pre-ACE the year that I taught you. Nuclear chem. We actually use this formula in nuclear chemistry as well. It looks like this. So there's a formula you can use for half-life. It's A equals A to the 0, 1/2 to the n. And you may want to have the formula on hand. You don't technically need to have it for this unit, but if you are studying for the Olympiad, half-lives is definitely a topic that's there. So you may want to go ahead and write this down. And this is actually the same exact thing that we did here, if you think about it. Our initial concentration is 1. We're looking for our final concentration. And we would do 1/2 to the number of half-lives. Were we told the amount of half-lives? Yeah, we were told that it was 8. So the 8 would technically distribute here. But what's 1 to the 8th? 1.
Disgusting.
With math.
So it would be 1 times 1 over 2 to the 8th, which is what some of you were able to successfully deduce in the first place. It would just be the same thing, which is 0.00391. But yeah, there's a formula you can use to come up with this. Technically, I just wanted to go over this with you for you to understand what is the idea of half-life in the first place. So what is it? It's an amount of time it takes to have half the amount you originally had. In a first order reaction, the amount of time of the half-life does not change. So this is actually expressing to us a first order reaction. And one of the stranger things I think in this lesson, but if you had all of the full equations, I think it would make more sense, is that depending on the order of reaction you have, the time it takes for each half-life is going to possibly change. And that's how you're going to determine what your order of reaction is. And we're going to see that shortly. Isa.
Does it being the limited reagent or not affect the rate, whether or not it affects the rate of reaction?
I'm assuming that if it's the limiting reactant, if it's a first order reaction, then it does. If it's a 0 order
What I mean is, if you have a reaction happening and one of the reactants is not the limited reagent, you change the concentration. Can that affect the rate?
If it has an order of 1 or 2, yes. Yes.
Is the half-life of substance like specific to each reaction, or is it always the same?
Depends on the half-life specifically depends on the order of reaction. Like how long or short your half-life is, whether it increases or decreases depends on your order of reaction. Yes.
Does half-life change with temperature? Right?
That's a good question. That depends. Does temperature or pressure alter the shape of your graph?
That's what I was asking.
Okay, so just in a different way. Sorry, I didn't get that. But no, I don't think so. Because it doesn't affect the shape of your graph. It affects only your value of K. It doesn't affect the graph itself. All right, so this is the part that you're gonna have to, I think, just for Cambridge straight up memorize. But like I said, you could look deeper into it. There are formulas that help understand why this is so a little bit better. Even the graphs kind of give it away. In a zero order reaction, what's gonna happen is your amount of time for each half-life decreases with time. Meaning that your first half-life is longer. Your second half-life is a shorter time. And so if we were to calculate, let's say that this was 1 half-life, and then this was half the concentration, and this was another half the concentration. I think this might illustrate it. In a zero order reaction, this is the length of time for your first half-life. I'm going to write here T1 half. And then this is the length of time for your second half-life. What happened? So I basically approximated what 50% of the initial was here and what 50% of the second amount was. So a quarter of the original. What happened to the length of time of the half-life from the first to the second? It decreases, right? It's a shorter amount of time. And so that happens in zero order reactions. When I have the graph of the concentration versus time, the amount of time of the half-life is going to decrease. So first half-life would be the longest time, and then the times will get shorter. First order reaction, it may not be as easy to see, but we'll actually see first order in one of our practice questions. Here our half-life is constant. This means that our first half-life will be the same length of time as the second half-life, which will be the same length of time as the third half-life, so on and so forth. The amount of time does not change for the half-life, meaning after every, for example, 30 seconds, you have half the amount you had before. And then it just keeps happening after every additional 30
So wouldn't
seconds.
that mean that you'd never
You never reach zero.
like what happens when you have one atom? What happens when you have one atom?
Technically, you reach
Uh,
the end of what you can have, right?
you know our theorist?
Assuming that you can actually, measure singular atoms. So they just are like, it's basically not there anymore.
Oh, you know this guy
So
Kowalski?
it
Yeah.
limits.
All the evidence support his theory.
And then
Like,
second order,
like, but that, like,
half-lives increase with time. So here, if this is our initial amount, and then let's say we half that, our first half-life would be here. And then what if we half this amount? We would go like here. I think it's kind of hard to see, but it does get a little bit longer with time. And if we half this amount,
right here.
I don't know, it increases with time. It's kind of hard to see from that graph, but it's the opposite situation to zero. So it goes decreases with time, stays the same, increases with time. And so when you draw your lines for your half-lives, you're going to have to use this concept to figure out what order of the reaction you're given is.
What third order?
It would be sharper, like very complicated.
Like,
What you would do
yeah,
in
this
IRL is you would basically plot it on an Excel or like a Google Sheets, and then you'd get a linear regression line, and it would help you figure it out. All right, so checkup 9. This comes from the textbook. I had debated whether to keep this question in or not. Not because it's a bad question, just because I'm not great at graphing on a board. But I graphed in advance, so I figured I'd keep it in just in case you were asked to graph yourself. So in this checkup, they ask you to plot a graph of your reactant versus time. Go ahead and start plotting. I'll help you figure out where your numbers should be. So this is 0. This is going to be concentration. This is going to be time. And in order to answer the question, you've got to be able to graph it. So we'll go back to A in a moment, but use the data in the table. Plot a graph of that thing versus time. C6, H5, N2Cl, which we'll learn what this is. It's, I believe it's a diazonium salt. We'll learn what that is in Unit 6. But we're plotting the concentration of that, diazonium salt. Anyways, this thing versus time. 0, I went 2, 4, 6, 8. If you'll recall, you want to fill at least half your graph on both sides. So I went 0, 2, 4, 6, 8, where each of these lines represents 0.4, 0.4, 0.8, 1.2, 1.6, and 2. And then on the time axis, I went to 2000. Yeah, I went to 2000. So this would be 0, 500, 1000, 1500, and 2000. And then you start graphing. So I'll give you a little bit of time. Which one? Okay, sure. I'll give you a couple minutes to graph it yourself, and then I'll graph it when we get closer. I'll give you about 3 minutes to graph it. And the reason why I think it's still important to do this exercise because you have to make a line of best fit. And you need to remember how to make lines of best fit. You don't like lines of best fit? Paper 5. Non-zero chance it shows up on paper 4. But paper 5, there's 100% chance you have a graph.
Good.
I don't know if I've ever seen a paper 5 that doesn't have a graph. And for you to like calculate the slope.
And I know it's like supposed to be difficult or something. I don't know why so many people hate it. Our lines of best fit supposed to be difficult. I don't see why people hate it so much.
It just depends on the person. Let me see.
That will like deduct points or marks if we don't use reading, right?
You should definitely use a ruler because there will be points for what I'm going to show you how to do after this. You'll definitely need a ruler. Graphing will probably be something that takes a significant amount of time on your paper 5, actually. Just making sure you read the lines correctly.
How like strict are they when it comes to graphing marks?
They're pretty strict in terms of if you miss it by a line, it's wrong. Like if it's one line up or one line down from where you said, it's wrong. So it has to be in the correct general area.
Does graphing have like arbitrary board? Assuming you got to like calculate certain points.
Yeah.
Okay.
All right, I'm gonna go ahead and start graphing it because I need to have it to show you what to do next. So I have 0 and 5.8. I have 4.4 and 200, which I believe is here. No, that's 100. And then I have 400 and 3.2.
Isn't that 120 or 150?
No, 100, 200, 300, 400, 500. Okay. The next one I have is 403.2, which is here.
I have a different scale on the other one. So
But our final answers should be similar at the end. Depending, you just have to fill your graph carefully. The next one is 602.5. That would use it right there because this is 2.4. 800, 1.7. 800, 1.7. 1,000, 1.2. 1,200, 0.8. 1,400, 0.5. That's here. And then 1,600, 0.3. That's like there. All right, so that's the general shape of the graph you should have. Is that what you got? Something that looks like that? The next thing is the line of best fit. This line of best fit should not be made with a ruler. Why not?
What?
Because it's a curved line. And a ruler will only give you a straight line. So because it's a curved line, it is not appropriate to use a ruler here. You actually have to kind of like curve it yourself. So
Then why is it called a line of best fit?
because you're trying to fit these points the best you can. Again, this would be much better done on a computer that fit it for you, but that's not what we get for a Cambridge exam. We get, paper. So how we do it. But if you were to actually take on a STEM major when you go to college, university, this would largely all be done on computer now. All right, so now that is worth typically 2 marks. Usually just to graph it is usually worth 2 marks, like on a paper 5. Let's take a look though. I want to go back to A because there's this question and it's an older question. But I think it's still an important one to address. How could we actually monitor this reaction? Like what kind of measurements could we take here to figure out what's going on? To measure the rate of reaction? What could we do? What could we measure in the product side specifically that could help us figure out rate of reaction? Yes.
I'm not sure, like, I don't know what are. We could measure the volume of the next.
Yes. Yeah. You can measure the volume of gas being produced. That's one thing that you could actually physically see because aqueous is not changing phases, but gas is a change in phase. And you can actually, and we will look at a technique before the end of the year, school year, on how we can measure the volume of gas. Hopefully, if we get the time, I can show you a lab with it. But you can measure the volume of the gas being produced. And so then we've got this. The next question is why I decided to keep this, because this is a very common type of question asked on Cambridge exams. From your graph, find the value of 2 successive half-lives. What do we mean by successive? Successive means one right after the other. So like first half-life and second half-life would be 2 successive half-lives. The last time we saw that word successive that I remember is when we went over ionization energy. If you recall, when we went over ionization energies, when we said we had successive ones, it was the first ionization energy, then the second ionization energy, then the third ionization energy. So successive just means in order. And so what we're going to do is we're going to find the value of our first half-life and the value of our second half-life. Well, how are we going to figure that out? What is half-life again? The time it takes to have half the amount you started with. So how could we figure that out from a graph? Don't we have a starting amount? Wasn't it 5.8? 5.8 was our starting amount, right? So what would the time be when we half that amount, according to our graph? So what would we do? Instead of 5.8, go to, what's half of 5.8? 2.9. So go to 2.9, which is like there. And now is when you use a ruler. At 2.9, you would draw a straight line. That is not straight. But you would draw a straight line with your ruler to here. I think my line of business is not great. It's actually wrong, but not wrong. That's when it's better. Tell me what you got. I had gotten 475 when I did it earlier.
That was not me.
500.
Did you get 500?
500, right? For each. Sure, it's 500.
I don't know. My line of best fit was much better on paper, I guess. This is my line of best fit on paper. I got 475. So should have been somewhere in that area.
Yeah, 500.
And so the idea is that you draw a line, like right here, and then right here. And so I got 475. So I got 475, 2.9. So when my concentration is 2.9, the amount of time is 475. Half your concentration again, what do you get?
1.45.
So half of 2.9 would be 1.45. So find 1.45 on your graph. 0.4, 0.8, 1.2, 1.6. Should be somewhere in this general area, right? Somewhere in this general area, 1.45. And find that number on your graph. When I did it earlier, I had actually gotten 950 when I did it on my personal graph. And you can allow yourself a little bit of room for error here because you drew your graph. You'll see in the Cambridge question that follows, they'll have one already drawn out for you, which will make your life much easier than drawing it yourself, possibly making a mistake with the tangent line and then not getting the appropriate answer. But the concept here is the following. When I half the concentration, how much does the half-life change by? 475 the first time and 475 the second time. Because if I add 475 plus 475, I get 950. So what you're supposed to come up with is that the half-life time is the same. So each successive half-life is the same amount of time, which means that the order of reaction would be what? So order equals 1. Because when you have a first order reaction, the amount of time for each successive half-life will be the same as the time as the last successive half-life. Yes. Question? It is supposed to be first order. Like I said, the one that I drew was better. That was on my paper. It did give that. All right. The next question I want to show you is how this shows up from Cambridge on a paper form. So they pre-drew it out for you so you don't make mistakes on your graphing. So they give you a reaction, they show you a graph, and they tell you, and this is actually, I think, a recent question. They're very nice to you. They tell you the reaction is first order. This can be confirmed using the concept of half-lives. First of all, can you explain what is half-life? And this is one of the only definitions, if not the only definition, for this concept. So what is half-life? And so you don't even have to say that it's the limiting reactant, it's just time taken or concentration of reactant to become half. Of the initial concentration. So it's just the time it takes for the concentration to be half of what it initially was. So that's the first point. The second point is the one that I really wanted to show you. How can you show your working on the graph to determine the half-life? So it says here, determine the half-life, show your work on the graph. So how would we do that? What do we have to prove to get the half-life? How do I show it on the graph? My initial concentration here is 0.25. So where would I need to find the half-life at what concentration? 0.125. So this is 0.1. This is 0.11. Right? This is 0.12. This is 0.13. So where's 0.125? At the halfway mark here, right? So then we would make a line with a ruler to this spot on the graph, that spot right there. And then where would we go next? What's the other spot with the ruler I need to go? So draw a line here with your ruler. And then what else do I need to draw? Is that an alarm? Is that the alarm for the experiment?
Yeah, it is.
I thought so.
It is, look.
Yes. I actually am going to test that soon.
Yeah.
I know what you're talking about. It's coming. The other line is right here.
It finally came.
So what number is that? 150. So writing that it's 150 with the evidence of the two lines on the graph is what you have to do for the mark. If you don't put the two lines on the graph, the one that goes from here to here and down, they don't give you the mark. If you just said 150 without the lines on the graph. So this is what they meant by show your working on the graph, was showing how you got to that half-life. Half the concentration, go to the spot on the graph where that time is correlated. That's how you get it. All right, so then the next question. Suggest the effect on the half-life if the initial concentration is halved. No change. Because it's first order. The answer is no change, just like that. Use the graph to determine the rate of reaction at 200 seconds. Show your work. So what would we do now? Use the graph, determine the rate of reaction at this specific amount of time. That's an instantaneous rate of reaction, but at that point. at 200 seconds, what would we do? Tangent line times. So now we go to 200, we draw a tangent line right here, and we go like that. Make sense? Because we wanted that specific rate at that specific amount of time. So they want you, yes.
If we find the equation of the graph, can we find the derivative to then find the slope at each point?
So how would you find the equation?
Because the equation,
Yes, you can use calculus. The quick answer is yes. If you had the equation, yes. With the, yeah, it would work. I believe it would, yes.
How can we find the equation?
That might go to the video.
you have the initial and then how much it changes by.
You need, I think, the integrated rate equation, which is the thing that I said that Cambridge leaves out that's in the AP curriculum.
Oh, you could finish some two.
All right, use the graphic by B to find the rate at 200 seconds, yes.
Sorry, wait, get the half of again?
How did I get the half-life?
Yeah.
I took the initial concentration, I divided it by 2. Then I found that time. Yes?
Yeah.
Okay, so tangent line. I think this is 0.17, somewhere around there. 0.17 and 0. And the other coordinate would be, I think that's 485? 485? Something like that. Something like that. And then it's y2 minus y1.
That's fine. And
I think it's 485.
fine.
Something like that. Somewhere in that range. They said that anything that you got that's between 4 times 10 to the negative 4 and 5 times 10 to the negative 4 was acceptable as correct. Units. Minus 1. Rate equation, they give it to you. Use your answer to C1, which I got was approximately 4 times 10 to the negative 4, to calculate the value of the rate constant for this reaction. So given that we know the rate is this, how can we find K? What concentration would we use for N2O5 is the question. Like, this is a concentration. How do we know what concentration to use? How did you get that? At 200 seconds, the concentration is 0.1. You're absolutely correct, Samuel. So 0.1. So this would be 0.1. Does that make sense? When the rate is this at 200 seconds, yes. Yeah, it's rounded. It was 3.54, something like that. When the concentration is 0.1, the rate is 4 times 10 to the negative 4. So solve for K. So 4 times 10 to the negative 4 equals K times 0.1. I'm just making sure, once again, does everybody know how I got 0.1? I know you do. 200 seconds, that where we got the rate. At 200 seconds, the concentration was 0.1. That's why we're using 0.1 for the concentration. And so it would just be 4 times 10 to the negative 4 divided by 0.1. It's first order, so it's 0.004. And the units are? What's the units for K? Ramon?
S to the negative 1.
Correct. Because it's first order. So the molarities cancel. So this is actually how it shows up on a Cambridge test. There's one more thing I want to cover before we go. Technically two. This next question is an older question, but I wanted to bring it up because it is an interesting question that could definitely show up on a test. They give you an experiment in which whatever reactant you have has a concentration of 2 times 10 to the negative 4. They tell you the rate of reaction is 1 times 10 to the negative 4. And they tell you to assume the rate of reaction is constant for the first 0.2 seconds. Could you draw a graph to show how the concentration varies for 0.2 seconds? What would we do? We've got the initial concentration. We know that it's 2.0 times 10 to the negative 4. How could we figure out how the concentration varies for 0.2 seconds? Anybody have a guess? Ramon, go ahead.
Use the initial rate to kind of graph it like
I would actually use the initial rate. You're absolutely correct. But I would use it with the time because we know how much the concentration is changing with time. So find out how much the concentration changes in that amount of time. How could we do that?
Take the slope from the initial and the rate. Or no, the rate is a slope.
I would say to just use it like this. Does that make sense? I have 0.2 seconds that have passed. I know that every second I will gain 1 times 10 to the negative 4 of product, lose 1 times 10 to the negative 4 of reactant, assuming that they go 1 to 1. So then you multiply these two numbers, which gives me 0.2 times 10 to the negative 5, I think. Or 2 times 10 to the negative 5. Yeah, 2 times 10 to the negative 5. So what does this information actually tell me? At 0.2 seconds, what's happened?
And how much? Okay, so that's the decreasing concentration.
That's the decreasing concentration of reactants. So this is the decrease in concentration of reactant. I've got my initial amount of reactants, 2 times 10 to the negative 4. So does that mean I can now find my amount of reactant at the end of that 0.2 seconds? So find concentration at 0.2 seconds of your reactant. So then this would be 2, and these numbers are kind of gross. 2 times 10 to the negative 4 minus 2 times 10 to the negative 5. I definitely suggest doing this in a calculator, but and some of you may want to do it in your heads, I don't know. I get 1.8 times 10 to the negative 4. Can that be put on this graph? Where? This is 1.75, so this must be 1.8 right there. So at 0.2, it's 1.8, so right there. Listen, this is kind of a gross question, but that's what it is. Those are the only 2 points that you need to get. You could get more points if you wanted to. Like you could find the concentration at 0.1 seconds, you could find the concentration at 0.05 seconds, but do you have to for the mark? No, why not? Why don't you have to get any more points than 2?
For it to be constant.
Because it's constant, which means the slope's not going to change, which means it's a constant decrease.
Couldn't you find the point at any other second and then draw the line?
You could, in the mark scheme though, they say they want the first and the last point. So I would just do the last one, the one at 0.2 seconds. I would say it then enters a gray area where the examiners fight over whether or not they're actually going to give the point for that. Maybe a bod. And so you just draw with a ruler a line through there, and that's your slope. That's it. That's all you do for this question. There's a couple more points to this specific question. Deduce the concentration of the product at 0.2 seconds. Remember I mentioned that the amount of decrease of reactant was this amount, 2 times 10 to the negative 5? Wouldn't this also be the increase in the amount of product? So if I start with 0 product, this would be 2 times 10 to the negative 5. So we're assuming we don't start with any product. So this would be 2 times 10 to the negative 5. The decrease of the reactant being the increase of the product. Because they said this is the product at 0.2 seconds. And then they say after 20 seconds, ClNO2 no longer changes. The concentration just stays the same. It no longer changes. How could that be? In what scenario would the concentration no longer change? Go ahead,
You
Alexander.
run out of Beno.
Nope.
Maybe because the agent works out.
Nope.
You ever check equilibrium?
That's the answer. So the reaction reached equilibrium. Because equilibrium is the spot where your concentrations of reactant and product no longer change, they stay the same. Reaction is still occurring, but it must be going both ways. Like your reactants are turning into products as your products are turning back into reactants. So you've reached equilibrium, yes.
If the limit of the agent works out, it becomes 0.
Yeah. The rate would turn to 0, yeah, because you have no more. All right, last checkup, and this is, like I said, it's a little bit oversimplified, but that's what we have for the Cambridge standards here. This is a little bit, they oversimplify the math a little bit because they're only giving you first order reactions. So there is an equation that you do need to memorize. And it's the one that's right here. If I have a first order reaction, all I need to know is the K value, and it gives me the half-life. And they are related in this way. The time of the half-life is defined as the number 0.693 divided by K. This is an equation that you are being asked to memorize. There are other half-life equations for 0 order and second order reactions, but you do not need to know them. That one you gotta know. And it has been showing up fairly often on recent exams. It's not difficult to solve. It's just remembering that this is something you need to know. This is a formula that you just straight up gotta know. So it says use the formula, which they would not give you on the Cambridge exam. They ask you to just find the half-life. To calculate a value for the rate constant of a reaction, its first order has a half-life of 480 seconds. So this right here is going to be seconds. The time you get here is seconds because K is in seconds. When you solve for whatever, well, first order of K is defined as second minus. So the time is in seconds. So all you would have to do to find half-life here, T1 half, is do 0.693 divided by K. What am I plugging in? The time, because I'm looking for K. So it would be 480 equals 0.693 over K. How do I solve for K? Switch them over. K equals 0.693 divided by 480. So K equals? I get 0.00144. Second time. And there's one more question like this. Trying to see if I have enough time to sneak in the video. Last question. First order reaction has a rate constant of the following. Can you find the half-life? First of all, you need the formula. So the formula is T1 half equals 0.693 divided by K. This time they gave you the K. So you just plug in 9.63 times 10 to the negative 3, 4K. So T1 half equals 0.693 divided by 9.63 times 10 to the negative 3. Yes.
Question for the other formulas, random guess. Since this one is second, like the
First
unit,
order.
but since first order is only second, for the other ones, would we need to know the concentration to get the half-life?
It's not independent of concentration. That's right. It's not for the other orders.
So we could know it.
You don't need it here.
For the relation between the K and the alpha.
No, you don't need to know that here. You only need to know that K and half-life for first order is independent of concentration. That's why the half-life never changes. Integrated rate law, I believe, or the integrated rate equation can give you that information. I have a few minutes, so I'm going to go ahead and show you a quick video. I'm going to stop sharing. This may answer some of your questions. So before we go, a quick video from Professor Dave. I'm going to turn it down.
Kinetics is the study of reaction rates for power.